Welcome back to our discussion of the relevant metrics of photovoltaic energy conversion. So far, we have discussed a large number of metrics related to the cost, efficiency, and integration of PV. Now, considering our fight to mitigate climate change, we'll discuss some environmentally relevant metrics of PV. These include the carbon footprint of energy produced using PV. Earlier this week, we compared the carbon footprint of PV to those of other sustainable energy technologies. Naturally, the carbon footprint, expressed in equivalent grams CO2 per kilowatt hour, is not a fixed property. The footprint depends on the carbon emissions during the process of manufacturing and transportation of the PV modules. It also depends on how efficient those PV modules are at converting the available sunlight into electricity under real-world conditions. This visual, for instance, shows the carbon footprint of a state-of-the-art PV system located in the Netherlands when produced in China. The footprint is much lower than that of electricity from the grid, which for a large part is based on natural gas. Nevertheless, if that same PV system would have been produced in the Netherlands, using the Dutch energy mixture, the carbon footprint would have been about half. Moreover, if the efficiency of the PV modules could be improved to the currently projected levels, the carbon footprint could be halved again. The same is true for relocating these PV systems to a sunnier location, for instance from the Netherlands to Australia. Finally, the carbon footprint also depends on the PV technology that is considered. For the production of the thin film silicon power foil from Hyatt Solar, for instance, a lot less energy is required and therefore carbon emissions are much lower. As a result, the projected carbon footprint of a future PV system can already be realized today using this technology, despite lower conversion efficiencies. This brings us to our final metric for PV, which is another environmentally relevant metric. The energy return on energy invested is the ratio of the amount of energy required to produce a PV system to the amount of energy generated by the PV system over its lifetime. In this visual, the energy return on energy invested is shown for different PV technologies. The black markers and colored boxes indicate estimated values based on different references. It can be observed that thin film technologies generally have a higher energy return on energy invested than crystalline silicon, as they require less energy to produce. Also note that even the PV system with the most energy intensive processing, situated in the lowest yield locations, generate at least about 3 times as much energy over their lifetime as goes into producing them. You have probably noticed from the black arrow bars and the large size of the colored boxes that there's a very large spread in estimated values. Estimating the amount of energy required to produce a PV system, from the raw materials production to module manufacturing, transport, and PV system installation, is no easy task. Reported numbers can vary widely based on the assumptions of the authors. And as you now understand, the energy yield of the PV system over its lifetime also depends on many factors. As discussed earlier, the conversion efficiency, shading tolerability, and temperature coefficient influence the energy yield of PV systems, as does the location where the PV system is installed. In this visual, the energy payback time, another way to express the balance of invested to generated energy, is plotted for different locations. This analysis here is performed for a thin film silicon system, in case that system would be both produced and installed in that location. The energy payback time therefore changes both as a function of the change in irradiance, indicated by the equivalent sun hours, as well as due to a change in the local energy mix and material sourcing and transport. The latter causes the energy payback time of Jaipur and Buenos Aires to increase with respect to San Francisco, despite higher equivalent sun hours. The visual shows that the energy payback time of the system can vary by over a factor 2, depending on the location. Assuming a 30-year system lifetime and 20% energy yield degradation over 30 years, this system would have an energy return on energy invested in a range of 18 to 45, depending on the location. However, not only the used technology, real-world conversion efficiency, and location have an influence on the energy payback time. This visual shows that increasing the size of the PV system, ranging from residential systems to large-scale utility PV systems, can also decrease the energy payback time by a factor 2. Now time for a short summary. In the last few videos we have discussed a large number of important metrics for photovoltaics. Some metrics, such as the conversion efficiency, shading tolerance, and temperature coefficient of PV modules, are related to the power density a PV module can generate under certain conditions at different locations. Others, such as the reliability and cost competitiveness of PV, are related to the economic aspect of PV system design and application. Some metrics, such as the recyclability and abundance of material resources, are related to the terawatt scale implementation of PV. Yet others, such as aesthetics, the ease of installation, flexibility, the product weight, and the ability to cover complex surfaces, are related to the integration of PV on all available building surfaces. Finally, there are some environmentally relevant metrics for PV, such as the carbon footprint of a PV system in its manufacturing and the energy return on energy investment or energy payback time. It is important to keep these different metrics of PV in mind as you are introduced to the wonderfully elegant technology that is the solar cell. These different metrics are relevant when we discuss the solar cell design rules in this course. And they are especially relevant when we arrive at the advantages and limitations of the different PV technologies in the next course and the PV module and system design in the third course. Thank you for your attention, and I'll see you again in the next week.